Now into our last set of lectures for the semester. We'll be talking about orbital mechanics. And this, like many of the things we've discussed, is a big topic of its own. There are semester-length classes just on orbital mechanics, so we won't obviously get to cover it in the same depth. We'll just have two lectures. Today we'll talk about some fundamentals, understanding better gravity and changes in velocity as we move between different orbits. Next time, we'll talk about the orbit equation for a two-body problem. We'll get transferring between orbits and trajectories and such. All right, show the screen. Okay. So to start, let's just review. We've all seen Newton's law of gravitation. And it is that if I've got say two bodies of mass, here's one, here's another, and just by convention, we usually one is much bigger than the other, so we'll have a capital M for the larger mass, a lowercase m for the smaller, but that's not necessary. There'll be a force of gravity exerted, right, and it's actually equal and opposite. Okay, and the force of gravity is given. The magnitude is going to be g, which is a universal gravitational constant, times the two masses, divided by r squared, where r, of course, is this distance. Right, this is r, the distance between them. Okay, and that's the magnitude. The direction is always along this radial line, right? So pointing from radius to radius, those two masses, and g, the universal constant of gravitation, 6.674 times 10 to the minus 11th, and that's in newtons times meters squared over kilograms squared. Okay, so this is an equation you've seen before, but what it tells us, some important things that tell us is that this force is proportional to the masses and varies as 1 over r squared. So the further we move away from a body, that gravitational force is going to drop pretty quickly. Okay, well, let's talk about the potential energy associated with that. And so before doing that, we just got to, again, remind ourselves what a conservative force is, and a conservative force versus a non-conservative. A conservative force is one that is path independent. So gravity, for example, is a conservative force. That means that we only care about the relative position between two objects. We don't really care about how they got there. So for example, if this was the ground, and I was looking at my gravitational potential energy, and I was, say, this high off the ground, I don't really care if I picked that rock up and just took it straight up, oops, or if I picked the rock up and I waved it around and did a bunch of stuff and brought it to there. It has the exact same potential energy. In contrast, friction is non-conservative. So, for example, like, let's just say, let's draw, like this is my tabletop here, and I had, this little puck, like a little hockey puck or something here on the table. If I was to move one, let's say from here to this final position versus moving from here all over the place and then ending up here, even though they ended up in the same last position, right? So the relative positions are the same. The path to get there is very different. And of course, friction, that matters. I'm going to expend a lot more energy overcoming friction with this path than I do here. Okay, so gravity, of course, as we said, is a conservative. This is a conservative case, right? Gravity is conservative. So it doesn't matter how I got there. I'm going to have the same well, we say it's a conservative. It's going to give me the same potential energy, I guess we could say it. So in other words, if we have a conservative force, we can define what's called a potential function, which has an associated potential energy. This is why we can't do that for friction. I can't say what the potential energy of this hockey puck is due to friction. It doesn't, it's meaningless, right? I have to know about the path and I have to integrate across the path. But we can do this for gravity because it's conservative. Potential energy U, we'll use the symbol U for potential energy. It's minus G times M over R, okay? So the minus sign just comes from the definition, but you could think of it this way, that this is kind of relative to infinity. So if I go very far away, R becomes infinity, then this goes to 0, and I have no potential energy. And as I get closer, that becomes a bigger negative number. Okay, so the usefulness, the main usefulness of potential energy is that I just took what was a three-dimensional vector function, i.e. a force. Gravity is a force, it's a vector, it operates in 3 dimensions, right? And I've reduced it to this one-dimensional scalar function. That makes it much easier to work with because I can look at conservation of energy, for example, which is much easier than trying to deal with the general 3-dimensional field of forces and apply Newton's laws and such. Another way this is useful is we can think of what's called a gravity well. Let me just pull up a picture, for example. Yeah, so here's a good picture, right? This is from Wikipedia. Here's a picture. This is plotting that potential function. And so we can see that, it's going towards 0 as we go very far away, and then it goes down into this big negative number as we approach the center of mass of that massive object. So you can see, you think of it as it's pulling everything in to this big hole, right? And so we don't need to know where we are, just need to know these constants, right? The masses and our position R. We can compute that potential energy, and it's just a one-dimensional scalar function. So very useful. Okay, so the question is, and this isn't a trick question, it's fairly straightforward, but it's maybe hard to judge the magnitude. Imagine I'm going to the moon, right? I'm going from the Earth to the moon, and then I want to make the return trip from the moon to the Earth. Which is going to be easier? Is it easier to get to the moon, or is it easier to return to the Earth? Is it pretty close? Are they very different? What do you think? So here's a picture of the gravity wells associated with the Earth and Moon. And of course, as we saw, like little m matters, right? So we have to pick something. So it's going to vary a little bit depending on what we're looking at. This is for a 1,000-kilogram spacecraft. The relative trends would be the same, just of course that would be some scaling depending on the mass of the vehicle. So what we can see is that, imagine here I'm at Earth, it takes an enormous amount of energy to escape this potential energy, to escape this gravity well and get towards the moon. Once I'm at the moon, I've got that local dip from the moon. It takes some energy to get out, but it's way less, right? And then it's pulling me back into the Earth. So yes, it is probably quite intuitive, right, that it's easy to get back, but the scale of it may be somewhat surprising, right? It's very, very different masses, or the moon, or sorry, the Earth is much more massive. Okay, and that extends more broadly, right? So I don't have the numbers on the top of my head, but if we were going to Mars, it's something like just getting to low Earth orbit, that takes most of the energy, really, as compared to the whole rest of the trip. It's quite a bit. Okay, so let's get into some calculations here, things that we can do with Newton's law of gravitation. And first, also just by way of review, we need to look at some of these constants and how this will work on Earth. So by convention, one thing that we're going to do, remember in the law, I'll just write it here as the force of gravity, and this is the magnitude, because it's really a vector. Gmm over r squared. Well, if we're on Earth, G is a constant everywhere. If this is the mass of the Earth, then that's not going to change. So it's convenient as we're working around a body to just define a new parameter mu, which is just multiplying those two together. So mu for the Earth would be take the gravitational constant, universal constant, multiplied by the mass of the Earth, and we get 3.986 times 10 to the 14th meters cubed per second squared. That's just a convenience. There's nothing fundamental done. It's just to save us from multiplying those two numbers again and again. We call this the geocentric gravitational constant, the center around the Earth. The radius of the Earth, and this is not precise because the Earth is actually not a sphere. So the radius is ambiguous, but this is sort of a nominal radius, 6,371 kilometers. Okay, so if I was on the surface of the Earth, I'm just right here on the surface of the Earth, then the force that I would feel on the surface is going to be, and this is just again a magnitude, G times the mass of the Earth times the mass of me or whatever object I'm looking at, divided by the radius of the Earth squared, right? And when we're on the Earth and at the surface of the Earth, right, we like to call this mg. This would be g at say sea level, for example, or at the surface of the Earth. Notice that g then is equal to this thing, right? That's just a constant we like to use because these don't change for the Earth. Right? Of course, they vary for different planets, but on the Earth, we don't normally go all the way back to Newton's law of gravitation. That's inconvenient to have to multiply a bunch of numbers that are always the same for the Earth. And so we just call that little g, which is about 9.81. Right? As we said, the mass of the Earth is not exactly, or sorry, the shape of the Earth is not exactly a sphere. So it actually is going to vary somewhat. So that's a nominal value. It's also convenient to recompute g for different altitudes. So let's say I took my same scenario here, and I'm now, up here. I'm at some altitude where this is h. I'm at some altitude h above the surface of the Earth. I may not want to go all the way back to the law of gravitation and just work with little g, but of course little g is different. If we were looking at the equation, again, if I'm just doing the magnitude, it's going to be g, mass of the Earth, m, divided by the radius of the Earth plus h squared, right? Because that's the distance I am from the center of the Earth. So if we just combine those, if we take this definition of little g, right, this is little g, plug it into here, and simplify, we're going to get the following, that g is equal to g at sea level 1, times the radius of the Earth squared divided by the radius of the Earth plus the altitude squared. So that's just a quick way to not have to go all the way back, to take our 9.81 meters per second squared and add this factor to get how g is going to vary. So then we can just use mg like we're used to. But it's always safe to go back to Newton's law of gravitation if that's more comfortable. Either ways will work just fine. It'll work the same. Okay, so now we have a few smaller exercises we're going to do to kind of get comfortable with this and practice this a bit. So the first question is, what is the escape velocity from the surface of the Earth? So what does escape velocity mean? This means that if I was to launch a projectile, meaning I launch at some speed and I don't get to do anything after that, right? It doesn't have a rocket on it. So it can't accelerate anymore. It's just whatever I shoot it with, say I shot it out of this cannon or whatever, that's the speed it's going to start at, and I can't do anything else about it. It's just going to be subject to gravity at that point. And I want to get this projectile to go infinitely far away. Right? I want it to completely escape that potential energy of the Earth. Okay, so I would recommend using an energy approach. So we talked about what the energy is, the potential energy of gravity. So pause and take a few minutes to work this out. See if you can come up with what the escape velocity is for an object getting out of the Earth's gravitational pull. Okay, so if you tried that, remember again, I have, I'm going to use an energy approach. So here I am on the Earth, just shooting the projectile, and I'm going to shoot it way far away, right? I'm at infinity here. And when it's that far away, so it's going to start with some kinetic energy and some potential energy. So let's call this point 1, this is point 2. We're going to use the symbol T for kinetic energy. That's a common used one, and U for potential energy. So T1 plus U1 is going to equal T2 plus U2, right? There's nothing else acting on this system. I'm not shooting any other rockets, so there's just energy just conserved. I fired this projectile, it's just going to go. Nothing's acting, so there's a conservation of energy. My initial kinetic energy is going to be just 1/2 mv squared, whatever that mass that projectile is and how fast I shot it. My potential energy, if we go back, just remember the formula. This one minus G m over r. It's that potential energy. So it's minus G M M over R, right? Where R in this case is going to be the radius of the Earth, and big M is going to be the mass of the Earth. Okay, and so now as I go infinitely far away, my escape velocity is a velocity I need to just barely get there. So I don't have any excess velocity, so my kinetic energy is zero, right? I just barely got there, got no kinetic energy left. And my potential energy, now I'm infinitely far away, right? So this R term here is huge, so potential energy goes to zero. So I just barely got far enough away that Earth exerts essentially no gravitational pull anymore. I have no kinetic energy either. I just barely got there. Okay, so I can solve this for V. Right, I'm gonna bring this thing over to this. Whoops. I'm gonna bring this term over to this side, solve for V, and I get that V escape equals the square root of 2 times G times M over R. Notice that my mass, or the mass of the object I threw, canceled out. It doesn't depend on that. It only depends on the universal gravitational constant, the mass of the body I'm trying to escape, and how far away I am from that body. So in our example here, we're looking at the mass of the Earth, the radius of the Earth. We plug that in, we get, let's see, 11,183 meters per second. So that's like 25,000 miles per hour, extremely fast. Right? That's not practical. Rocket doesn't go anywhere near that fast at the surface. You'd have way too much drag and aerodynamic heating. It just would not be practical. But of course, this represents not what a rocket can do. So a rocket, as we talked about, it's going to accelerate, actually slow down for a bit, probably accelerate again. So we're going to accelerate through the atmosphere, especially as we get into the lower density parts of the atmosphere, we can accelerate further with higher speeds. This represents what we'd have to do with a projectile, right? It's just a good reference point to kind of know how much energy it takes to escape Earth. And it's quite a bit, okay? So this same procedure though, so here I'm just illustrating kind of this thought concept about what we call escape velocity, the definition of escape velocity. But this is the exact same procedure we can use to calculate delta V. Here, what we're calculating is a delta V. How much change in velocity do I need to impart to this thing, like a projectile or to a rocket? How much delta V do I need to add from this propulsion system to get to different orbits? And so that's going to be that exact delta V we used in previous questions, or previous problems, where we were trying to compute, use the rocket equation to figure out what our change, how much propellant we would need, for example, and so on. So this is kind of that process. We're going to get to delta V, is that we got to figure out what our kinetic energy is going to be at the different states, and then we use the different potential energies from gravity. All right, so before we go to the next one, just a conceptual question, somewhat of an aside. If I want to launch a rocket, we've talked about that there's a certain delta V we're going to need to get. And in our case, we don't generally want to go to infinity, right? I want to go to low Earth orbit, or I want to go to some other planet or whatever, so my delta V is not going to be the same. But I compute some delta V. The question is, where do I build a rocket launch facility? Where's the best places for me to build a facility? And using what you know about maybe where some of these launch centers are at, why are they located at those locations? So just take a couple minutes, think about that. Why are they located where they are? Well, so of course we know we've got here in the US, right, we have some launch facilities in Florida, Texas. Why are these locations? Well, first of all, we want to be near ocean, right, where we can launch over an ocean. So when things come down, they're going to not be over land, right, where people are going to be. But that doesn't answer the question, well, why don't we have them in California or up in Washington or somewhere like that? Why are they on the East Coast, and why are they further down? So there are two reasons here. One is, remember, the Earth is rotating. So if I had a launch facility up at the North Pole, the rotation of the Earth doesn't help me at all, right? Whereas if I have a launch facility near the equator, because that Earth is rotating, I actually already have some velocity. And that's about, it's like 450, 465 or something meters per second at the equator. So, I mean, That's a small number compared to this, but it's still significant. That means I don't need quite as much speed if I'm launching closer to the equator, because the spinning rotation of the Earth is already giving me a boost. That also means I want to launch to the east. I want to launch in the direction that I'm rotating instead of against it, because then I'd have to overcome that rotation. So I launch to the east. So that means I want something that's near the equator, and I want something that has ocean to the east of me, so I can launch that way. And that's why, again, in the U.S., Florida, Texas, those fit that kind of criteria where we can launch over a body of water close to the equator, as close as we can in this country at least. Okay, so let's do another problem. Let's say I am now up, I want to get into a circular orbit. So here's my body, let's say Earth, and I'm a satellite or a rocket or something, and I want to go around in a circle. Okay. However I got there, I want to know how much velocity I need to maintain that circular orbit. So I've got to figure out, this kind of goes back to this question. So here I calculate escape velocity, but now I want to launch a rocket and not just get to some, random super far away place. I want to get to this orbit, but I want to get there so that I have a certain amount of velocity so I can maintain the circular orbit. What is that velocity that's required to maintain that circular orbit? And we'll specify what that radius is, right? We'll just call it some generic R for now, right? I want to get to this R. What velocity do I need? Okay, so pause, take a few minutes or so, see if you can solve this. Okay, so this one is easily, so if we go back and think back to physics, right? What's the acceleration that I need to maintain a circle? Remember that it's F equals mv squared over R. That will give me, that's a centripetal acceleration, right? If I want to maintain a circle, I need the force centripetal to be mv squared over R, okay? So what's F in this case? At least magnitude-wise, pointing towards the center, gmm over R squared, and I need that to equal m, and this is my mass, the mass of that vehicle, e squared over R, so the masses cancel out, and I get v is equal to the square root of gm over R, okay? So this is, looks very similar to this. It's 1 over the square root of 2 less, so it's about 71% of the escape velocity. So that's still quite a large number. Compared to I still need about 70% of that velocity to maintain this circle. All right, so one more problem, and I'm not going to do this right now. I'm just going to introduce it. We're going to do it when we in class, but if you're not going to be there, and I guess when I say in class, that's going to be on Zoom since we're moving to virtual after Thanksgiving. But if you're not going to be able to be there, then it's something you might try on your own. So here's the question. So we have a satellite. It's going to be in geosynchronous orbit, and that means that it's at the right altitude so that it matches exactly the rotation of the Earth. So it's going around the Earth at the exact speed that the Earth is rotating, so that it just stays over the same position, near the equator, so that we can say monitor something. Sometimes it's useful to have a satellite that just stays in the same place relative to the Earth. So the question is, how far away from the center of the Earth, and normalize that by this radii, but how far away from the center of the Earth do we need to place that satellite so that this just happens? Okay, so again, I'm not going to do this right now, but you try it on your own, or actually we'll try it in class. You don't have to try it now, but if you're not going to be there, you can try it on your own. Okay, so that's going to be it for today. Next time, we're going to talk about trajectories for spacecraft, rockets, and things. Look at some different types of trajectories that are possible and how we calculate how we move from one trajectory to the other. So we'll see you next time.